Good morning and welcome. I'm Al Karitz, Director of Applications and Support for Electron Microscopy Sciences. I will act as moderator for this series of webinars. We'd like to ask you to take time to respond to our brief poll. Electron Microscopy Sciences and Quorum have been together many decades of excellence in sample preparation. Today, we present the second in our series of webinars examining three distinct sample preparation workflows for electron microscopy. Today's tutorial, presented by Dr. Helena Bland is about conditions required to produce ultra-high resolution EM images and elemental analysis using thin film deposition. Dr. Helena Bland joined Quorum Technologies as an applications specialist in 2024. She completed her integrated master's degree in chemistry with biological and medicinal chemistry at the University of York. Following her degree, she worked as a research assistant at the University of Helsinki, specializing in carbohydrate synthesis. Helena completed her PhD in chemistry at the University of Sussex, where she synthesized leptin peptides and investigated their impact on the aggregation of beta and tau amyloid using TEM. In her role at Quorum Technologies, Helena delivers technical expertise and guidance to the company's global customer base, working closely with users to understand their specific workflow requirements and recommend tailored application-based solutions. Through her support, Helena helps customers optimize their performance of their systems and adapt to evolving scientific and technical needs, achieving reliable, high-quality results in their work. Without further delay, I give you Dr. Bland.
Hello, everyone. Thank you so much for that lovely introduction, Al. As mentioned, my name is Helena. I'm an application specialist at Quorum Technologies, and this is our second session in our three-part webinar series on sample preparation for electron microscopy. Today, I'm going to be focusing on thin film coating for ultra-high resolution electron microscopy imaging and analysis. There we go. So as Al mentioned, EMS and Quorum have been working together for over 20 years, and we specialize in electron microscopy sample preparation. This covers sort of four main categories. The first is critical point dryers for the dehydration of high moisture content samples for SEM. We have glow discharge for the surface modification of TEM grids. Cryo for the rapid freezing of samples prior to SEM, and then finally our sputter coating and carbon evaporation systems, which we're going to be talking about today. Just to give you an overview of what we're going to cover in this webinar, I'm going to start off by talking about what is sputter coating and the sort of theory behind sputter coating and carbon evaporation, and then moving on to why it's so important in our sample preparation process. We're then going to be focusing on how we go about choosing our coating material, depending on what we want to see from our sample. And then also going into depth about what the difference is between carbon rod and carbon fiber evaporation. Finally, I'm going to be covering some frequently asked questions that we get at Quorum and EMS, and then opening up the floor to take any questions from the audience. So to start off, I wanted to emphasize why coating is so important when we're thinking about non-conductive samples in our electron microscope. So it's pretty evident from this image that we have here that we're not seeing what we want to actually see of our structure. So this is a pollen grain that's on top of a spider web, but you wouldn't be able to tell that because this image has been so poorly produced. So what we can see in our image is we have charging, which is these bright spots, we have drift, we have distortion, and we also have sample damage. And this is all mainly caused by the fact that this sample has not been coated prior to going into the SEM. So when we put a non-conductive sample into an SEM, because we have our electron beam aiming at our sample, if we don't ground the sample correctly, the electrons will build up on the surface and they'll have nowhere to dissipate to. This buildup of electrons results in this effect known as charging, and it produces these bright spots so that we can't see our images so clearly. So coating is super important for a number of reasons, but the main one is to enhance that conductivity to prevent charging. It also improves signal to noise ratio, helps to reduce beam damage, and also helps to enhance secondary electron emission. Sputter coating itself is the technique that we use for putting down a thin layer of metal onto our sample. And just to go a little bit behind the principles of how sputter coating works, we have our vacuum chamber here, which will have a target, which is our metal, where our coating is going to be coming from. And then we place our sample underneath that target. The chamber is attached to a vacuum pump as well as a gas inlet. We put our chamber under vacuum and we introduce our argon into the system, which is what we typically use for sputter coating. We then apply a voltage to our target, making our target act as the cathode and our sample act as the anode. This applying of a voltage results in the formation of electrons, which then collide with our argon atoms to produce argon ions. It's this combination of electrons and argon ions, which is known as plasma. Because our cathode is negatively charged, our positively charged argon ions are attracted to our cathode. And it's the collision of these ions with our target that results in the deposition of a thin layer of metal onto our sample. So that's how sputter coating works, but what do we actually need to think about when we're considering what kind of material we're going to coat with? And there's a few things that we want to take into consideration. The first is something known as grain size. So the grain size is the smallest sort of size of grains that are produced during the coating. So the smallest islands of growth dictate what the grain size is. And in general, the smaller the grain size, the higher resolution and higher magnification imaging you're going to be able to do. This is because a smaller grain size is less likely to obscure your sample. Ionic radius size can impact the way that our forms film, so whether they're densely packed films or finely packed films, and this can also impact how high magnification we can go to. We want to think about our secondary electron yield, so how bright our image is going to be coming off of our sample. The physical properties of the metal itself, so is it actually suitable for sputtering? Then, of course, when we think about a lab, we also have to take into consideration cost. So I've actually got the prices here in pounds because Quorum Technologies is based in the UK, but you get the general picture, which is that chromium is approximately £1.12 per gram, whereas iridium is £116.95 per gram. So it's 100 times more expensive. So of course, that's going to come into consideration when we're looking at purchasing our target materials. And then finally, we want to think about the capabilities of the coater that we have. Is it a rotary pump coater or is it a turbomolecular pumped coater? And how good vacuum can we actually get on the system that we have? These are the metals that we typically use for sputter coating, and they all have a lot of things in common. So the first thing is that these all have high electrical conductivity. So we're able to produce a layer that's sufficiently conductive that we can reduce charging on our samples. Second, they are thermally and chemically stable, so there's not going to be any issues during our sputtering process. They all have fine grain deposition, so we're not going to see grains of coating on our samples. And finally, in general, they have low oxidation during and after deposition. We can then split those metals into two separate categories. We have our noble metals and our oxidizing metals. If you have a rotary pumped coater, you can only coat with noble metals and not with oxidizing metals. This is because if you have an oxidizing metal in a rotary pump coater, the vacuum is not going to be sufficient to prevent oxidation of that metal. But there are plenty of advantages associated with noble metals. So in general, the grain sizes are suitable up to around 150K. They have good secondary electron yield. And a benefit is that obviously we can store our sample. So if I coated my sample with gold, I put it in the cupboard for 3 months, and then I came back to it a few months later, Yes, there'd probably be hydrocarbon contamination on it, but the gold itself would not have oxidized. So I could then put it back in the SEM and image that sample again. Whereas if I have an oxidizing metal, such as chromium, if I coat it and then I leave it in the cupboard for 3 months, by the end of that 3 months, I'm going to have chromium oxide on my sample. And this is much less conductive than chromium and therefore not suitable to prevent charging in scanning electron microscopy. So then with our oxidizing metals that we require a turbomolecular pumped coater for, we have smaller grain sizes, so we can look towards oxidizing metals for our higher magnification imaging. They also have good secondary electron yield. The only disadvantage associated with them is that, of course, we need to have a turbo pump coater in the first place. And also we need to think about that our samples, the coating might be oxidizing after we've coated. So I mentioned one of the most important things about selecting a material is thinking about the grain size. So you can see quite clearly, all at the same magnification and the same nanometers of coating, that we have quite a stark difference between our gold coating, platinum, and iridium coating. So we can see that with our gold coating, we have a larger grain size, which means that gold is not suitable for higher magnification imaging. So when you get to around 80K, you will start to see gold coating on your samples. And that's why if you are doing ultra high resolution and high magnification imaging, you need to be looking towards metals that have smaller grain sizes, such as platinum, and smaller yet, such as iridium. The ionic radius of the metal can also impact how the films are formed on the sample. So in general, a smaller ionic radius will have stronger bonds between the ionic radii, which will mean that we have denser, finer grained films. So if I have a zoom in on these samples, you can see that with our gold, we have quite separated individual grains, whereas with our iridium, it's slightly more densely packed. And then with our tungsten, we're actually struggling to see the coating layer because it's sufficiently densely and finely packed. So in general, a metal with a smaller ionic radius will produce a denser, finer grained film, so it will be better for the higher magnification imaging. Once we've selected our material, we then need to think about how much we're going to put onto the sample. As a general rule of thumb, we tend to say that you don't need more than 10 nanometers of coating for most materials, particularly if you're doing using a FEGSEM. This is because, well, obviously it will be sample dependent, but a lot of the time, like overcoating can be an issue as well as undercoating. And that's pretty well demonstrated in the images on the screen. So if we look at our far left image, we've got 2 little coatings, so that's 0.2 nanometers. And we can see that we've still got charging on the sample, and we've got some beam-induced contamination here on the image. Then if we move over to overcoating, you can see that at 10 nanometers, we're actually obscuring the morphology of our fibers. So you can see all of the coating along the back as well as on the fiber itself. And we're not actually seeing what our sample looks like. Whereas when we have 2 nanometers of coating, we're able to see the morphology, but we're also not being affected by charging or any contamination buildup. Finally, we want to think about the vacuum that we're actually coating our samples in. So the better the vacuum, the more uniform a coating you can get. So this is why whenever people are working with FEGSEMs or FIBSEMs and they're going beyond 100K magnification imaging, you really want to be using a high vacuum coater so that you can make sure you have the most uniform deposition possible. You can see that with a poor vacuum, you get this very uneven sort of blotchy deposition. With a slightly better vacuum, it's a little bit improved, but with our high vacuum systems, you have a very fine coated deposition, which is very uniform across the sample. This is just a side note about removable coatings. So sometimes metals can be selected based on the fact that they can be removed using chemicals. So silver, nickel, and copper are 3 examples of metal coatings that can be removed with sort of dilute acid solutions in order to return to the sample to what it was before without the coating. So sometimes that's something that people like to do so that they can get their samples back so that they're not coated anymore after they've done their imaging. Moving on from sputter coating, we have our carbon evaporation. And carbon evaporation tends to be used for when we want to do SEM and we want to do elemental analysis, or if we're looking to coat TEM grids. So carbon evaporation is a lot more of a straightforward technique. All we're doing is we have a carbon source and we are applying a voltage, which is resulting in the evaporation of carbon from the surface. And we have two types of carbon evaporation. We have carbon fiber evaporation and carbon rod evaporation. So just to go through the differences between those two different types of evaporation, because depending on what you're actually wanting to do with your sample will depend on what kind of evaporation is best suited. Our carbon fiber evaporation is a pulse technique. So that's just that we are applying pulses of current through our carbon source in order to produce evaporations in pulses of coating. This we tend to recommend for general carbon coatings such as EDS, and it's also particularly suitable if you've got very heat sensitive samples. Carbon fiber evaporation works super well if you're doing lower magnification imaging. You're not too worried about having very thin coated layers, and you're just doing more sort of general work. It works completely fine. If you're wanting to do sort of ultra high magnification imaging and you're wanting to have sort of quantitative analysis, then you really need to move towards carbon rod evaporation. So carbon rod evaporation can be done two types of ways. We can do pulsed, similar to the fiber, where we're putting pulses of current through our carbon rod. And this is quite useful if you want to do particularly thick coatings for SEM. And then we have our ramped carbon rod recipe. So our ramped carbon is where we are slowly increasing the current so that we can control the deposition of that current really finely. So this means that we can put down to as low as 1 nanometer coatings of carbon, whereas that's quite hard to control with our carbon fiber because that's just going to be coming off in pulses that might be between 2 and 5 nanometers. So using ramped carbon is particularly important when you're doing the sort of higher magnification imaging, and particularly if you need to have precise control over how much coating you're actually putting onto your sample. You can also see there's quite a clear difference between what coatings look like with carbon fiber versus carbon rod. So our carbon fiber produces a much more amorphous layer, whereas our carbon rod has a much finer grain coating. And this is why if you're ever doing ultra high magnification imaging, you really need to be using carbon rod coating and not carbon fiber coating for your samples. Vacuum also influences the coating. So you can see that with a better vacuum, we have a much finer deposition. It's also important to note that with carbon rod evaporation, the rate of coating is also drastically improved with the better the vacuum. So if you have a better vacuum, you will coat faster compared to a not as good vacuum. And similar to sputter coating, there's such a thing as too little or too much coating. You can see when we've got a thin coating on this sample, we can see sort of structure, whereas with our thicker coating, we've completely obscured that structure. It is important to note, though, that carbon coating doesn't give as good a contrast as metal coating. So if you are primarily looking to image something and it's not important for your elemental analysis to use carbon, then you'll actually get better contrast with your images with metal compared to if you use carbon. But obviously carbon is mostly used for elemental analysis where we're wanting to not obscure any important peaks in our elemental spectra. So I now just finally wanted to talk a little bit about the frequently asked questions that we get at Quorum and at EMS. So the first one that we have is, what kinds of stages should you use with what types of samples? So with our turbo pumped coater, our TurboQ, it automatically comes with this tilt stage that's suitable for stubs, up to 6 stubs, either at a flat position or at a tilted angle. And the benefit of this is that you can have slightly more 3D structures, which will allow you to give you slightly more even deposition on those structures. We then have our rotocoater, which is our planetary stage. So a planetary stage has rotation in 2 separate directions, which means we get super uniform coating along a complex 3D structure. So definitely if you're working with powders or anything like sort of butterfly wings, anything with like a complex 3D structure that has like ridges, then you want to think about having a planetary stage such as the rotocoater. We then have our 4-inch wafer stage, which is designed specifically for wafers or for any samples up to 4 inches in diameter. And finally, we have stages suitable for slides as well as for cover slips, but I don't have that shown in the images. I just also wanted to note when we're talking about mounting our samples, it's very important that we fully ground our samples when we mount them. So a lot of the time, if you just stick a sample onto a carbon tab, you're not actually properly grounding all of that sample to the surface. And it means that you will still get charging within your microscope. So sometimes then it's important to use something such as carbon cement, like late C, so that you can actually make sure there is a electrical connection between the sample and the stage itself. The next question we get is, why is it important to service a coater, and do coaters need servicing? So we do recommend that coaters are serviced around once per year, unless the coater is less frequently used, in which case every other year should be sufficient. The reason that coaters require servicing is largely due to a decrease in vacuum performance over extended use. So that's usually just that the O-rings, for example, that help to seal the vacuum have degraded over time, or we've got contamination buildup in our chamber, which leads us to the sort of main advice that we give to people, which is something really important that no one wants to hear, which is that regular cleaning can help to reduce the need for instrument servicing. So the buildup of contamination in your chamber will do a couple of things. It will reduce the vacuum performance. It will lead to more likely getting sort of plasma errors. So buildup of contamination around the sort of target area can cause plasma errors. So we have difficulty igniting our plasma. And it can also result in sort of chunks of coating ending up on our sample where it's just literally flaking off from the shutter, for example. So it is really important that you do clean your coaters, and we recommend that you clean coaters with lint-free cloths and ethanol or isopropyl alcohol. And then if you have a particularly sort of thick buildup of metal on your chamber, you can consider using sort of dilute acid solutions such as hydrochloric acid. But it's really important that you're sort of regularly checking your O-rings to make sure there's not debris on those O-rings, because it will mean that it will be harder for you to achieve the vacuum you need to get that really good coating. Finally, I have the question of, can you sputter coat in air? And the answer is technically yes. Of course, you can actually sputter coat in air. It works similarly to an argon, except for we obviously have oxygen and nitrogen atoms. And then those are going to be our ions that are bombarding our target. However, then comes the question, should you sputter coat in air? And the answer is sometimes it's acceptable, but for this particular talk, which is about ultra-high magnification imaging, it's not really acceptable. So the reason for that is that, so when we're working with something like gold that doesn't really pick up oxygen too much, we can kind of get away with it. So you can see the difference here. We've got an argon, in argon coated with 5 nanometers of gold, and then in air. And you can see there's a tiny bit of charging going on that you can't see on our argon coated sample. So if you're doing a sort of low magnification imaging, so that's less than 50,000, then it should be okay to do gold coating in air. Whereas when we look at a material like platinum that isn't oxidizing, so it's not that when we have oxygen introduced into the chamber that the platinum itself is oxidizing, it's that there is oxygen sort of interacting with our platinum surface, which will result in beam-induced damage on our samples. So you can see here, when we've swapped to platinum, we actually are seeing a problem with our coating. And this problem will get worse depending on what metal you're using. So obviously, if you're coating with an oxidizing metal like chromium, you absolutely cannot use air. But also when you get to those higher magnifications, this impact is going to be even more extreme. So if you're using a FEG-SEM, then you really shouldn't ever be coating in air. But if you're using a tungsten SEM, you're only going up to 50,000 magnification. You can coat with gold. It is sort of an acceptable thing to do. So just to let you know a little bit about our products at Quorum and EMS. So we have a turbomolecular pumped coater known as the TurboQ, and this is either the TurboQ S, TurboQ E, or TurboQ ES. And this is our instrument that we recommend for ultra-high resolution electron microscopy. So the reason for that is it's got a turbomolecular pump, so it's able to get to much higher vacuums compared to our rotary pump system. So this goes down to 1 × 10⁻⁶. So we can get much more uniform coating. Because it's turbo pumped, it means that we have access to coat with oxidizing materials such as chromium. And it is also optimized for carbon rod evaporation, which is what we want to use for our high magnification carbon coating. Just to tell you a little bit about the system itself and a few of the features and benefits. So it comes with a tilt color touchscreen with a USB port to allow for updates and also to remove any information from the coater itself. It's very easy to use, so our history is all stored on the instrument, and you can create customized recipes as well as use previously saved recipes from our little recipes portal. It also has different options for login, so you can have different levels of users log into the instrument, so you can have different people in a lab of multiple users having access to different things on the instrument. It has all of our stages for our TurboQ are rotation stages, because rotation is very important when we want uniform coating. And as standard, it comes with a tilt stage, so that allows you to do flat samples as well as slightly more complex 3D samples. It then has an extended height chamber, which is great for easy cleaning, so you can easily remove that chamber. And it also allows for carbon evaporation and sputtering processes. So with carbon evaporation, we prefer to have our sample further away from our carbon source, because the evaporation of carbon rods can cause heat to build up within the chamber. So we use this sort of short stage to keep our sample far away from the carbon source. We then have, you can see in the tall configuration, where we've got it set up for sputter coating. And then we have our film thickness monitors automatically come with the system. So that's a quartz control measurement monitor, which allows us to control the deposition onto our sample. As standard, these instruments can either be just evaporation systems, just sputter coating systems, or both. And if it's a system that's both, it will automatically come with a sputter head as well as a carbon rod head. And then there are options for having different kinds of inserts. So even though we do recommend carbon rod evaporation for higher magnification imaging, you can still use the carbon fiber head with this system. So if certain users prefer to just use it for more general coatings, you can get a carbon fiber head. And in addition, we can have a glow discharge head for both cleaning as well as surface modification. And finally, a metal evaporation head. So thank you so much for listening and coming to this session. Just to give a little shout out to our next session, which is going to be on June 17th at 9 a.m. And that is going to be on cryofib-sem techniques for lamella preparation and volume imaging. Thank you so much for listening. I'm now going to sort of open up the floor to any questions, and I'll just stop sharing my screen and hand back over to Al.
Thank you, Helena. It was very informative. One question that comes up quite frequently is, can you sputter with a carbon target? So
technically, it is possible to sputter with a carbon target. However, we would never recommend sputtering with a carbon target. This is for a few reasons. The first one is that carbon has a very low sputter yield, so it's actually very difficult to sputter with carbon in the first place. It would take a very long time to deposit a sufficient layer. But also the layer that we deposit with carbon sputtering is nowhere near as fine a grain of a layer compared to our carbon evaporation, which is why we don't use carbon sputtering for electron microscopy. So the layers that are formed with carbon sputtering will not be suitable for our electron microscopy applications.
Okay, thank you for that explanation. Any other questions from the attendees?
There's some in the question and answer session.
So what is the gas used for carbon deposition? You may have mentioned it, I missed it. Thanks.
So we don't actually use a gas for carbon deposition. So when we do our carbon evaporation, what we're doing is we are doing that under vacuum. So we're removing all the gas from the chamber. However, we will use a gas to vent the system. So for example, nitrogen, so that as the system is vented, it's vented in a clean way to prevent contamination.
Yeah, thank you. And a second question regarding film thickness monitoring, is the readout given in real time?
Yeah, so our film thickness monitors read out down to 0.1 nanometers coating. So you can basically have a recipe where you specify how much coating you want. Say if you want 5 nanometers, you tell the system I'd like 5 nanometers. And then in real time, you'll be able to see the thickness increasing as it's deposited onto the crystal. So you'll be able to see, it will also report a rate. So it will say like it's coating at 1.2 nanometers per minute, for example. So you can also sort of work out in your head how long it's approximately going to be. So yeah, it is given in real time.
Thank you. For TEM thickness, and I imagine this is regarding carbon coating, is anywhere from 4 to 16 nanometers viable in our system?
So with TEM, for coating onto TEM grids, I typically wouldn't recommend coating that thickly onto them. So with TEM grids, you typically do want a fairly thin layer so that you're actually able to see your sample on the TEM. But we can, so with our carbon rod evaporation, we can coat down to 1 nanometer. So I would say like 16 nanometers is probably too thick, but 4 nanometers might be okay for TEM grid. But yeah, you can, I mean, you could technically coat with that on the using the system if you wanted to. You could put down 16 nanometers. I think it would be too thick though.
Thank you. The next question, can you explain the need for carbon coating for EDS and TEM?
Yeah, so people typically like to use carbon coating for EDS because when we're looking at our sort of elemental spectra, carbon is typically doesn't interfere with too many common peaks that we might be looking for in our elemental analysis. So that's why carbon is often used as a standard, but it is also possible you can use other metals for elemental analysis. However, it really depends what kind of elements you're looking for in your analysis, whether it's going to actually obscure what you're looking for. The need for TEM is that, so when we have, it's the same as SEM, where we still need to create a conductive layer. So you can either buy TEM grids that are pre-coated, or you can coat your own TEM grids. So obviously buying pre-coated TEM grids, you don't need to coat them. They've already got coating on them. But if you buy grids that aren't coated, then you will need to coat them. And the benefit of coating your own grids is that you have a little bit more control over how much you deposit. So you can sort of change it for different samples. And you can also ensure a very clean deposition, because obviously like when we have pre-coated grids, they've probably been sitting around for a while. So you can have a sort of freshly coated layer on your sample.
Thank you. Preventing heat damage while carbon rod evaporating, what is the optimal distance from the source to the grid?
So I don't have a number off the top of my head, but so I mean, if you're coating a grid, you might not necessarily want to deposit directly onto the grid. So there's a few ways that you can coat basically onto mica, which is like a silica sort of, yeah. You can coat onto mica, and then from the mica, remove that layer and then put it onto the grids, and that's less likely to cause cracking onto the grid. So sometimes we don't directly coat onto the actual grids themselves, but coat onto mica and then move that onto the grid because it's less likely to damage the grids. But in terms of distances, we have sort of the two setups with our sputter coating and carbon evaporation system, where we have the carbon coating is much lower down in the chamber. It's much further away. What that number is off the top of my head, I'm not sure, but it is a much greater distance, where we have like short stages that are built specifically for the carbon evaporation process.
Okay. Are there any other questions from our audience today? Nope, not at the moment. I thank everyone for your attention and participation today. And thank you, Helena, for the high resolution, high quality tutorial today. It's always interesting to hear how you can improve your results in your microscope, whether it be TEM or SEM. Join us next time for our final webinar in the series, which Helen already talked about. That's it. I don't see any more question. Okay. So one more question, snuck one in here at the end. What are the size of the sputter targets?
So our sputter targets for the Quorum EMS systems are 57 millimeters in diameter, but different coaters will have different diameter targets. And then in terms of, you can get different thicknesses of targets. So the thicker the target, the longer it will last. But obviously buying a thicker target will be a larger outright cost compared to buying a thinner target.
And I might add that Quorum has stuck with the same diameter target size, I think, for over 25 years that I've been involved with Quorum and their product lines. So if you have an older, Emitech or coder or an earlier Quorum coder, you can, if you upgrade or replace that instrument, you can keep your targets because they're completely transferable from one system to another. Now we have a vacuum question. Vacuum of 10 to the minus 5 for carbon evaporation, would there be cause for large flakes?
So not necessarily large flakes. You wouldn't get as fine a deposition at 10 to the minus 5. I would say 10 to the minus 5 is really the minimum you'd want to do with carbon rod evaporation. It would be better at 10 to the minus 6, but 10 to the minus 5 is generally acceptable. So yeah, not large flaking. That wouldn't be an issue. You don't tend to ever get large flaking from carbon rod evaporation. But your deposition rate would definitely be slower at 10 to the minus 5. And it would also be not as good a quality as it would be at 10 to the minus 6.
Yeah, exactly. And if I can add my experience, I used to do a lot of freeze fracture and rotary shadowing, and you can achieve coatings of carbon which do have a tendency to flake and curl up, but generally above 20 nanometers in thickness, which is, for all intents and purposes, for your traditional TEM and SEM coating, way too thick. If you're making replicas, ideally we wanted 15 nanometers of carbon to stabilize the platinum replica. But this is, an old technique that's hardly done anymore. Yeah, you wouldn't want thicker carbon for multiple reasons. One, you can't see through it very well with the microscope. Two, it will have a tendency to flake. And in worst case, it actually curls up and causes some other issues. Is it possible to obtain a carbon head if you happen to have lost them? We lost one for a Q150 TES, which is discontinued. Helen and I can, talk about this if you wish. The thing of beauty is consistency going forward with the Quorum line. All the earlier Q series inserts still work with the TurboQ series. So the Q150s may be discontinued and not in production. However, their inserts and sputter heads and evaporation heads are all still in production and available All you have to do if you're here in the US is ask me, or contact Quorum in the UK directly, and they can provide you a quote and availability for those devices. We don't leave our customers behind when we move into the future. We have solutions that are continuous, and we don't give up on old instruments so easily. Okay, I think that will conclude our discussion today. I'm available for, discussion. I'm happy to work with you here if you're in the US based. And certainly my colleague, Helena in the UK can answer a multitude of your application questions. We're happy to serve you and support the Quorum product line, producing excellent results for you in the laboratory. Thanks again for your attendance and attention. We'll see you on the next one.